BigO notation is the language programmers used to talk about how fast code is not in seconds, but in how the work grows as the input grows. It's the single most important idea for reasoning about performance, and it quietly underpins every video in this series. Let's make it concrete. BigO answers one question. As the input gets bigger, how does the running time grow? We care about the shape of that growth, not exact numbers, so we follow two rules. Drop the constants. O of 2n is just O of n. And keep only the fastest growing term. N squared plus n is just n squared. It's the worst case at scale. Here are the classes you'll meet. Fastest to slowest. O of 1, constant, the dream, same cost no matter the size. O of log n, logarithmic, have the problem each step, like binary search. O of n linear, touch every item once. O of n log n, the best general sorting. O of n squared, nested loops. And O of 2 to the n, exponential, the danger zone. Picture searching this array for a value, one cell at a time. With n items, in the worst case you check all n, that's linear, O of n, double the array, and you double the work. Now compare that to a sorted array with binary search, where each step throws away half the data. Same input, completely different growth. Let's see growth in code. Grabbing the first element is O of 1. Instant, whatever the size. A single loop over n items is O of n. And a loop inside a loop, comparing every pair, is O of n squared. 100 items becomes 10,000 steps. The nesting is the tell. Logarithms show up whenever you have. Binary search on a sorted list is O of log n, 1,000,000 items in about 20 steps. And the workhorse of sorting, like Python sorted, is O of n log n, a linear pass across a logarithmic number of levels. Whenever you split and recombine, watch for that log factor. A quick Python cheat sheet, because the data structure decides the cost. List indexing and appending are O of 1, but checking X in a list is O of n. Dictionary and set lookups are O of 1. That's why they're everywhere. Inserting at the front of a list is O of n. Use a deque for O of 1. Pick the structure, and you've picked your BigO. BigO is the lens behind every choice we've made. Why hash maps beat scans, why sorting unlocks binary search, why the LRU cache fights for constant time. Once you can see the growth curve, you can predict performance before you ever run the code. That's the whole game. Thanks for watching the series.